Okay, welcome back to the next part of the aliphatic nucleophilic substitution reaction. So, I would like to start with the phase transfer catalyst. So, what is phase transfer catalyst? Basically, when you perform a reaction in a two phases, for example, you are performing organic reaction. One of the compound is soluble in organic solvent, other compound does not dissolve in organic solvent. So probably Suzuki coupling, you probably heard about this if you ever. This is a cross coupling reaction, and there we use toluene, methanol, and then water. Three different solvents. It's very important here. So to understand why we need to use those different kind of solvents, because uh, or some of the molecules are soluble in organic solvents, some of the molecules are soluble in water. Okay, now to bring them together, we have methanol there. Okay, so methanol will bring both of them together, and the reaction may occur in the methanol medium. But this can be avoided by using, we have a phase transfer catalyst. Okay, so when you perform the substitution reaction, consider we have the aliphatic compound which is soluble in organic solvent, and we have a nucleophile that is soluble in water. So how they can react if they don't come closer or to each other? So we need a phase transfer catalyst that changes the phase of one compound and take it to the other phase. Okay, so that is what we call as a phase transfer catalyst. Okay, so in a biphasic reaction, it could be liquid-liquid, liquid-solid, or liquid gas. Okay, there we have to use this kind of phase transfer catalyst. The role, the carry reactant from one phase to the another. That is a very important thing. That is why we call phase transfer, changing the phase of the reactant. Importance, increases the rate of reaction by bringing the reactant in the same phase. Okay, so that's what I was telling you. Okay, because if they are in different phases, they will no collision. So if you think about the collision theory in chemical kinetics, okay, so reaction kinetics, so if there is no collision, no reaction. So you have to bring them in the same phase where the reaction should happen or should occur. Examples, there are certain examples like ammonium salts, they are very commonly used, phosphonium salts, crown ethers. The reason is that these compounds soluble in aqueous as well as in organic solvents. So that is the most important thing, and that is why it is used as a phase transfer catalyst. So if when you are using the phase transfer catalyst, always remember that my catalyst should be soluble in both the phases. The same thing in Suzuki coupling, we have a toluene, we have a methanol, we have water. Methanol is miscible partly with the toluene, but highly miscible with water. So they can, yeah, the water can, methanol can bring them together into the reaction. So the same thing here happening. Okay. Okay. So let's take a very good example. So for example, we have a RBR. Yeah, we have nucleophile there. Okay, so let's talk about, we have the aqueous phase, we have interface, and we have the organic phase. What we have in the aqueous phase, we have sodium cyanide. So RBr is my the reactant, and what I want to do is that I want to do this reaction, and this is my catalyst. Okay, which somehow it will form later on. We'll do it. Basically, I will show you some example of it there. So my sodium cyanide is here. Okay, and my which I have to take it to the organic phase. Okay, so first what happened is that you use the cationic species with the bromide. So there's first ion exchange happen between the your catalyst, which already having with the, like if you take the ammonium salt, so ammonium bromide, tetrabutyl ammonium bromide you take. So tetrabutyl ammonium bromide will exchange the ions with the bromide, so the sodium cyanide. So sodium cyanide now it becomes sodium bromide and tetrabutyl ammonium cyanide. Now this tetrabutyl ammonium cyanide is what soluble in water as well as in the organic. Now this will take to the organic layer. Now you see my cyanide and my bromide, they are in the same phase and the reaction can happen. So basically sodium cyanide, which is not soluble in organic phase, it is actually exchange the anions or cations, or it sodium cyanide exchange the cations, it goes to the catalyst, and then the catalyst take it to the organic phase, the reaction happen, and then the then that CBr, which is the bromide, comes back again into the exchange. So that is what is the cycle going on, and this is the interface. So this is what we call as a phase transfer catalyst. Okay, now this reaction I actually performed by myself. So I will show you the practical example that I have seen. So I wanted to replace this bromide with a cyanide. Okay, the reaction actually performed at 80 degrees Celsius. It requires 5 hours, and you got a roughly 60% yield. 60% product we can isolate it from the starting material. Okay, and we got so many side product. However, what I did basically, I used 18 crown 6. So I will show you the example of the structure. Is the structure is given here, 18 crown 6, and you can see sodium can bind over there, and your cyanide will be free. Okay, and that can easily react with your nucleophile. So when I perform this with 10 more % as a catalyst, room temperature, 1 hour, I got 90% yield, very clean conversion. You can see what's the change. It changes the temperature by about 50 degrees. So you can say 80 degree and becomes 30 degrees. So I performed in US. So basically the temperature roughly 28 to 30 degree in the summer. So that was the temperature. If you say 30 degree, so you can reduce the temperature by 50 degrees Celsius. Okay, and then we have the yield 90%, where you had 60%. We had 5 hours required. Now we require only 1 hour, and very clean conversion. It's a very clean conversion. You just have to do very quick column chromatography to remove some of the very like a little bit of starting impurity, but it is not visible in TLC plate. Okay, so this is very clean. So the catalyst, what it does is that I am using that solvent acetonite, right? So in acetonite, right, this compound is partly soluble. Okay, but sodium cyanide is also partly soluble. But this catalyst, when we have the catalyst will the phase transfer catalyst will bind with the sodium, and then this is soluble, highly soluble in sodium cyanide. It's immediately soluble. So when you add crown ether, you just start some time that everything will be soluble in acetonite, but this is not soluble. So only time taking because to dissolve this starting material. That is what. Okay, but reaction is very fast. Okay, so that is what we call phase transfer catalyst. Okay, now talk about that. Sorry, okay, it's coming now. So when you perform the reaction SN1 or SN2, how can you predict that which mechanism it should follow? So let's recap the things. So in case of SN1 reaction, we're starting with the any substrate. That first is the redetermining step, where it release the carboanion, the leaving group, which is in the form of anion. Then form the tight ion pair so that it can react again back to form the starting material. Then the nucleophile can come from both directions because it is a planar sp2 hybridized planar, come from the top or bottom. You can have racemic mixture. In SN2 reaction, it's a single step reaction, the substrate coming from the back side, and you have a transition state, and you get the product which have inversion. So this is the reaction energy profile diagram for the SN1 reaction. You can see we have a two-step process. First step is a leaving of your leaving group, and then or departure of the leaving group, formation of the intermediate, and then the nucleophile comes and you got the products, racemic mixture. And this is a single step process. Your transition state is the here it forms, and then you've got the product. So here you've got inversion of chirality. Now if you have the situation like which mechanism is operating, how you can judge it by seeing the substrate. So if you see the substrate, if it stabilizes the carbocation, then we can say okay, it's a SN1 reaction. If it does not, then you can say it should follow the SN2. If you take an example, tertiary butyl like halide and methyl halide. Methyl halide cannot stabilize the carbocation because CH3 plus is unstable, so it should follow the SN2 mechanism. When you go for the tertiary butyl halide, then we should follow the SN1 mechanism because the backside attack by the nucleophile is not possible there. Okay, so next comes solvent. If you use polar protic solvent that we have discussed, in polar protic solvent, your anion, which is a leaving group, should be stabilized by hydrogen bonding. But in case of if you use the polar protic solvent in SN2 reaction, what would happen? Your nucleophile will be solvated, then your reaction will be slowed down. Okay, so that is very important. So you should use polar protic solvent for SN1 mechanism, for polar aprotic solvent for SN2 mechanism. Okay, nucleophile. We do not need a good nucleophile for SN1 reaction, but we really need a moderate to good nucleophile for SN2 reaction, because in SN2 reaction nucleophile involves in the transitions, oh sorry, in the redetermining step. So it should be very good. Okay. Second, leaving group. So for SN1 reaction, the leaving group should be very good. If it is a bad leaving group, then you should not have the SN1 reaction, because it should leaves the molecule automatically. Okay, you dissolve the molecule in the solvent, it immediately clip the bond and you produce the carbocation. When you do the same thing in for SN2 reaction, the leaving group may be moderate or good. That is not that much difference. The reason behind is that you have a push from the nucleophile. So nucleophile will attack from the backside and that will kick out. So moderate is okay, moderate to good is okay. So and bad is always bad for both the reactions, both the mechanisms. Okay, so that is one thing. Now, there is another method to identify the mechanism. So it is called kinetic isotope effect. So you just right now, I don't know who are listening this lecture, if you have proper knowledge what is kinetic isotope effect. So basically, you can think of stabilization of carbocation by hyperconjugation. Okay. So if you replace this hydrogen with a deuterium, so this carbon deuterium bond is stronger than the carbon hydrogen bond. Now, if this is stronger, then so the energy will be less for the CD bond. So the stronger means the energy is less. Always remember, whenever we talk about stability, something is more stable means the energy is lower compared to the other one. Okay. Now, if your transition state is here somewhere there, so this will require some energy, this require more energy. More energy means the rate will be slower, and that is the reason when you have a SN1 reaction which forms the carbocation, that gives you the kinetic isotope effect by hyperconjugation, if the hyperconjugation at all involved there. Okay, so that you can also try to prove by using or calculating the kinetic isotope effect. In case of SN2 reaction, because there is no intermediate formation, so it is a concerted process, so you do not have such scenario that can stabilize the carbocation by CH bond breaking, then you should not see any kinetic isotope effect. Okay, so there is primary kinetic isotope effect, secondary kinetic isotope effect. So for carbocation we are talking about, it is a secondary kinetic isotope effect. So the value Kh by Kd, I am talking about the rate constant, should be for around 1, between 1 and 2. Okay, so that is what. So if it is showing such value, we can say this is SN1 mechanism. It does not show, it would be SN2 mechanism. This is another method of to prove that whatever you are saying. So see, the science always experimental evidences. So you have to, you can explain based on the situation, but you have to provide a clear experimental evidence. So these are left side, whatever I am showing, that all these substrate, solvent, these are proposed. There are no experimental evidence. This is the experimental evidence. So in kinetic isotope effect, if you measure, okay, yes, this is SN1 or SN2, you can easily see. But one thing that you may not always have the alpha hydrogen. So then it is, you have to follow something else. Okay. So there is some other things that there we can discuss later. Okay, so what is the take-home message? So SN2 mechanism is a single step and a bimolecular reaction. That's why it's SN2. And SN1 is a two-step process and unimolecular reaction involving one reaction intermediate. The bond breaking and bond making occurs simultaneously in case of SN2 mechanism. The bond breaking step occurs first, which is the redetermining step. Universal polarity occurs in the SN2 mechanism and nucleophile, you have a racemization in the SN1 mechanism, which is ideally but not always. You always have some inversion because the tight ion pair, and as I told you that before the leaving groups completely depart the molecule, you already produce sufficient positive charge on the carbon center, so the nucleophile start coming from the backside. So that is what it is. Then the relatively strong nucleophile required for that SN2 mechanism, and here nucleophile does not influence the rate. Steric crowding heavily influences the rate, because if you have a steric crowding, the nucleophile from the backside may not be able to come, because that will hinder its path to reach the carbon center. But steric crowding is not a problem for SN1, because you have a planar carbocation, it can either come from top or bottom. Then we have transition state is a less polar, and hence electronic effects are less in prominence over there, and stabilization of carbocation is expected here because you have carbocation intermediate, you will see there. Okay, so this is all about SN1 reaction and substitution reaction aliphatic compound. So we can discuss later about this regarding this particular topic more. There's some other topic left over like SNI and neighboring group participations. We will be discussing later. Thank you very much. I hope you learned something from this class.